Okay, so my name is Ray, and this is my colleague Max. And the overarching theme of our presentation is going to be about cooperation. So Max, do you think you could help me move this mat onto the stage so that the audience can actually see our demonstration? You ready?
Sure.
1, 2, 3, lift.
So what you just saw was us cooperating to complete a task, lifting up this mat onto the stage. And we can break down this task into 3 components that are necessary for cooperation. That's sensing, thinking, and communication. We both used our eyes and hands to sense the tilt and weight of the mat. And based on what we saw and felt, our brain made decisions on how much force we should apply using each of our arms. We also communicated to synchronize our actions. Ray said 1, 2, 3, and then we lifted together. Given these 3 essential ingredients, we were able to cooperate and act. In this case, we moved the mat, but you can imagine more complex and different tasks. It is now becoming economically viable to embed sensing, communication, and computation technologies in almost any physical device. Take, for example, your smartphones.
So it's becoming now possible to create artificially cooperating systems. Take, for example, future truck and car platoons. So each vehicle in this platoon uses its own sensors, computers, and communicates with one another to keep a tight formation on the road in order to reduce drag. It's kind of like cyclists in a peloton. Now, the benefit of doing this is that it increases the efficiency of the vehicles while reducing the cost on fuel. Notice also the scalability and the flexibility here. Any number of vehicles can move in and out of its platoon while still benefiting from the reduction in drag. What about using drones for mapping and surveillance purposes? So drones can be made to work together in order to map out a large area fairly quickly. And this might be important for time-critical tasks such as search and rescue operations, wildfire monitoring, etc. Using multiple vehicles, you can robustly and more reliably perform search and rescue operations. Now, in order to fully exploit artificially cooperating systems, there is a need to address the issues involved in its design and implementation. Now, the distributed flight array, which is what you see in this video, and originally envisioned by Professor Raffaele D'Andrea, was envisioned to be this artificially cooperating system. What it is a modular robotics platform consisting of multiple autonomous vehicles that are able to move around on the ground, self-assemble with its peers, coordinate with one another in order to move together, and once a sufficient number of them are connected, they can take off and fly. Okay, so I know what you're all thinking, or some of you might be thinking, yeah, this is just a quad rotor. I probably got one at home for my son. This is a quad rotor. That's the distributed flight array. This, on board, has a single computer and a single set of sensors, and it uses that to control each of its 4 individual propellers.
On this platform, however, the set of sensors and computers is distributed among the individual units. Just like how Ray and I cooperated to move this mat, each of the units uses its own sensors, own computer, and communicates with its peers in order to calculate how much thrust it should produce to keep the vehicle level in flight. This makes the system very flexible. In this video, you see different configurations made out of 6 units. Also, the platform is very scalable. We can fly 4, 6, 10, or even 100 of these robots. We want to emphasize that although each of the robots can produce enough thrust to lift itself off the ground, a single robot on its own is incapable of stable flight, much like a helicopter without its tail rotor. Only through cooperation, these robots can fly stably in air. To connect with its peers, each robot has magnets on its sides. The connection, however, is not very strong. This emphasizes that robots need to work together in order to prevent them from tearing themselves apart during flight. We'll now present to you a rather fragile configuration. Once the vehicle is up in the air, you'll see that there are very few connections, and it's almost a line. This is very hard to control and only possible because of cooperation. We have been asked many times whether it's also possible to self-assemble the array during flight, and as of this week, we can answer this question with yes.
Wow.
So today we have presented to you a system that shows the benefits of cooperation, and we have demonstrated that the whole can indeed be greater than the sum of its parts. Thank you.